Okay. So an automobile starter motor has an equivalent resistance of 0.05 ohms and is supplied by a 12-volt battery with an internal resistance of 0.01 ohms. What is the current to the motor? So here's a 12-volt battery, internal resistance of 0.1 ohms, and the motor, which is the load, is 0.05 ohms. So the current is EMF divided by R plus R. We'll multiply this by 100, 12 over 6 is 200 amps. So that's what it takes to start your motor. Now here's the deal. So oftentimes your terminals can get corroded, and that adds resistance to this. Okay, you get loose contact and stuff like that. If that thing adds resistance, let's say that became 0.05 ohms. Now the total resistance is 0.1 ohms, and the current drops to 0.1 ohms. It drops to 120 amps. So just a little resistance added there decreases the current quite a bit. And maybe it might not start your car. What power is supplied to the motor? So the power supplied to the motor is the current squared through the motor times the resistance of the motor. So it's 200 amps squared times 0.05 ohms. And that's 10 and 10 times that, 2000 watts. So then they say, what power is supplied to the motor? What is the voltage applied to it? Okay, so this is C. And B, the voltage that the motor sees is the current through the motor and the resistance of the motor. So that's 10 volts. So you see the terminal voltage is 10 volts. What the motor is seeing is 10 volts, not 12 volts. Because 2 volts dropped across the internal resistance. Okay. Okay, so there's C. And repeat these calculations when the battery connections are corroded. When the battery connections are corroded, and add 0.09 ohms to the circuit. So this would become 0.09, so that becomes 0.1 ohms. Okay. And so you can do the calculations. The current will decrease and all that kind of stuff. An 1800 watt toaster, a 1400 watt speaker, and a 75 watt lamp are plugged to the same outlet in a 15 amp fuse and 120 volt circuit. So even though this is AC, we're going going to do it as a DC. This is the toaster, this is the speaker, and this is the lamp. Okay, so it's outlet to a 15 amp fuse. What that means is you don't want more than 15 amps flowing in this wire because it would burn it up. So there's a fuse somewhere here. A current of more than 15 amps will burn that fuse, and that's easy to replace. Okay. All right, so this is, let's see what is the current the toaster draws when it's working by itself. We'll see what each of those guys draw. Okay, so there are all these see 120 volts. Okay, and power of the toaster is the voltage it sees times the current in the toaster. And the toaster is 1800 watts and the voltage is 120 volts. 2, 3, and that's 15 amps. So the toaster by itself is drawing 15 amps. And so when the toaster is working, if you turn on anything else, the current will be this plus this, which will be greater than 15 amps. So when the toaster is working, nothing else can work. Otherwise, you'll blow the fuse. Okay, so the current in the speaker power to the speaker divided by the voltage, 1400 watts divided. So the speaker itself draws 11.7 amps, and the lamp draws 75 watts divided by 120. So the lamp and the speaker can work together. Okay. But once the toaster is on, nothing else can work. Okay. So here's the circuit shown. Now, here's multiple sources, but they're in the same loop. So effectively, what this acts as is, see, this is a 12 volt battery, this is a 24 volt battery. So effectively, it's 12 volts in this direction. Okay. But we're going to use Kirchhoff's laws to solve it before we do that. What is happening? What do you think this circuit is doing? What is this thing doing?
The two voltage sources are generating opposing electric fields.
So this guy is recharging him. This is how you charge a battery. Okay. So if you drive a current in the opposite direction, if this is a rechargeable battery, you are charging that. All right. We'll use Kirchhoff's rule to solve this. But again, like I said, effectively, you could just say it's 12 volts in that direction. But all right, this is a closed loop, and we'll use the loop rule. Okay, we'll start off here and go around like that. So how many terms will we have?
8.
Yeah, so we're going to use this rule. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay. Huh? Okay. All right. Plus 12 volts. I'm starting here and going around. So that's plus 12 volts. Or let me write the symbols. Plus V1 and we'll say the current is flowing this way. So, and the current is going that. So you're going against the current. So that's plus I1, IR1 plus IR2 plus IR3. And what is the next term?
Minus V2.
Minus V2. Very good. And plus IR4 plus IR5. So this is really equal to I times R1 plus R2 plus R3 plus R4 plus R5 time equal to V2 minus V1. Like I said at the beginning, this is effectively acting like a battery of V2 minus V1. A single battery of that voltage is equal to I times R.
So can you like assume the current's going in either direction, or can you go, or can you only go one way? Like
Okay, so good question. So our friend here is asking what if had you drawn the current this way? Okay, so this way it's going to come out positive. Let's do this number. So this I is V2 minus V1 is 12 volts divided by the sum of the resistors, 10 plus 20, 40, 50, 60. 60 ohms. And so this is 0.2 amps. Okay. Had you drawn like Owing says, if you draw the current like this, the answer would have come out negative 0.2 amps. What does a negative current mean? It's,
flowing the opposite.
yeah, it's flowing in the opposite direction. Okay. So it doesn't matter how you draw it. If you drew it the wrong way, then you'll just get a negative answer. And in a real circuit, the current is flowing in the opposite direction.
Question.
Mm-hmm.
When you're doing your Kirchhoff voltage law,
Mm-hmm.
what's your logic for determining the signs of each thing?
When you're flowing against the current, you're going uphill, so that's positive.
Okay.
And when you're going across a battery, when you go from low to high, that's positive. When you go from high to low, that's negative.
That's so the opposite of what it seems it should be.
I'm just used to a different convention, but that makes sense.
Mm-hmm. Why?
It really feels like you should go plus when you're flowing with the current, you should go plus when you're going negative to positive.
Well, so no, think of it this way. Current flows from a higher potential to lower potential.
Gain, kind of back up.
Mm-hmm. Change in potential. Remember, electric fields point from higher to lower potential. Current is flowing in the direction of the. Okay, so here's a problem where we need Kirchhoff's rule. Okay, so here is a source in one loop, and here is a source in another loop. Okay. All right. So how many unknowns do we have? V1, I2, I3. 3 unknowns. So you need 3 equations. Okay. What is the easiest one to use? Junction rule. Okay. So how many independent junctions are there? There are 2 junctions. Here's one junction, here's another junction. But these 2 junctions are on the opposite ends of the same arm. So it's really they're not independent. Okay. So we'll use the junction rule here. I in equal to I out. All right, help me out.
I2 is equal to I3.
I2, I1 and I2 are flowing into the junction. Should equal I3, okay?
How can you tell that? I just thought we can.
You can just make an assumption.
No, these guys are flowing into the junction. There's the junction.
Oh,
And this guy's flowing out of the junction.
okay.
Mhm. And you see, let's come to this end.
I3 flows in, and I1, I2 flow out.
So it gives you the same equation, okay? So if you come to this end, I3 is flowing in, I2 is flowing out, and I1 is also flowing out. So it gives you the same equation. I1 is 2, I2 equal to I3. So there's one equation. We need two more equations. And how many loops do we have? 3 loops. So you can use any two of those three. So we'll keep it simple, L1 and L2. Okay, so I'm going to start here, go around like this. All right, I'm going to start here, plus V1. Minus I1R1. Plus I2R2 equal to 0. So V1, I1 is 2, 2 times 12 plus 6 times I2 equal to 0. There's equation 2. Okay, loop 2. Does it matter where you start? No. Okay. We'll start here. We'll go across. What is this? Plus V2. Then you're going with the current, so that's minus I3R3. And then you're going with the current, so minus I2R2. V2 is 21. R3 is 5, so minus 5 I3 minus 6 I2. There's equation 3. Okay, so what did we do? We looked at that circuit and we set up these three equations. And now you can solve these three equations. Okay. Everybody know how to do this? Okay. Do you want me to do it, or you guys are good?
Good.
A little more complicated. Okay, again, multiple sources, multiple loops. Again, here's one junction, here's another junction. Again, these are not independent junction, but here's an independent junction, and this is independent. Even, see, this junction is not on the other, this arm ends here. So you really have 1, 2, 3 independent junctions. So they can potentially give you three equations. How many loops are there?
4.
1, 2, 3, 4, 5, 6, 7, 100 million loops. Okay? So you can get many equations. All we have is 3 unknowns. Okay? So all right, V2 is an unknown. R4 is an unknown, okay. Okay, so if you use this loop, you see V2 will be the only unknown there. Okay. And you can solve for V2 right away. So we'll use this loop. We'll call it loop 1. All right, I'm going to start here. Anybody want to help me out?
V2 plus
Mm-hmm.
I3 I3R3 minus I5R5 equals 0.
Okay. So V2 I3R3 is 1 times 6, 6, and minus I3R4 is minus 12. So V2 is 6 volts. Okay. All right. The next thing we want to solve is V1. So,
Can you use that top loop?
I'm sorry?
Can you use that top loop?
Yeah. So whatever unknown, I guess we'll use the top loop again. Let's start here and go like that. So we'll call this loop 2. Okay, so let's start here. V1 minus I1 R1 minus I3 R3 minus I2 R2 equal to 0. I1 R1 is 24. I3 R3 is 6. I2 R2 is 12. 30, 42. Okay. And then R4, where is R4? Oh, there is R4. Okay, so now you have to use this loop, okay? So you see we didn't use the junction rule at all on this one. We only used the loop rule. Okay. So we're going to start here. I4 R4. So minus I4 R4 plus I2 R2 minus V2 equal to 0. I4 is 1, so minus R4. I2 R2 is 12 plus 12. V2 was 6. Okay. Do you want to see another one, or you guys got it? Hmm? All right. Whoa, 5 unknowns. I don't want to do this. I'm tired. Yeah. I1, I2, I3. Okay, so let's see. I1, I2, I3. Okay, how many junctions? Two independent junctions. Okay, so we'll use the junction rule. The junction rule says I1 plus I3 equal to I2. That's one. And then this junction says I4 is coming in and I3 and I4 are going out. So I4 equal to I3 plus I5. Okay, so those are two equations. Now let's use loop 1. Okay, so loop 1 will always start at the corner plus V1 minus I1 R1 minus I2 R2 equal to 0. So 12 minus 4 I1 okay. For L2, we're going to start here, go around like that, plus I1 R1 minus V2 minus I3 R3. So 4 I1, and I'll bring the V2 on that side. And minus I3 R3 minus 2 I3 equal to 5 volts. So equation 1, 2, 3, 4. And now loop 3. So loop 3, again, we're going to start here, go around like that. Plus V2 minus I4 R4. Oh, this is good. Equal to 0. 5 equal to 2 I4. There's equation 5. Okay. So you solve for I4 here. No, that. Okay. So 1, 3, and 4 just involve I1, I2, and I3. So you can solve for I1, I2, I3 there. You already have I4 here, and then I3 and I4 will give you I4. Okay? So you still have to do 3 equations and 3 unknowns. So equation 1, 3, and 4 will give you I1, I2, and I3. Okay. And then 2 and 5. I'll give you I4 and I5. All right, so a heart pacemaker fires 72 times a minute. Each time a 25 nanofarad capacitor is charged by a battery in series with a resistor to 0.632 of its full voltage. What is the value of the resistance? Okay, so we're just doing the charging part. So this is the charging part. Okay, so here's the voltage of the battery. Okay, you close it, and each time, okay, so to the full voltage, okay, 72 times, so 60 seconds divided by that, so t equal to 60 seconds divided by 72 times. All right, so if you look up your notes, the full charge, so here's how you remember this. Charge, voltage, and capacitance are related like that. So charge is, so, and that's the voltage. Anyway, so full charge corresponds to V times C, 1 minus e to the power of minus t over RC. RC is the time constant. Okay, so what they're saying is, so this thing is charging, firing 72 times a minute. So it fires when it gets, it's not fully charged, it's charged 0.632 times its full charge. Okay, so at this time, for this time, at Q equal to 0.83 seconds, this charge is 0.632 times full charge. This is the full charge, because t going to infinity, this goes to 0, and that's the full charge. Okay, did you guys understand that? All right, that's why they didn't give you the voltage of the battery, because this thing cancels. So 0.632 equal to 1 minus e to the power of minus, and I'll write t over tau. T is, okay. So e to the power of minus t over tau is that 1 minus this, and 1 minus that is 0.368. So now we'll take the log of both sides. So minus t over tau is log of 0.368. Tau is minus all right, and tau is RC. So R is 0.833 divided by C, and C is 25 nanofarads. Thirty-three mega ohms. That's the resistance you need in the circuit, so this thing can be charged such that it fires 72 times a second. And so if you want the heart to beat faster, you need to reduce the resistance. Okay? So if you reduce the resistance to 15 mega ohms, 16 mega ohms, how many times will the heart beat?
146?
44 times, twice as fast. Okay? So it's linearly dependent on that.
If you decrease it to what? Sorry.
So if you decrease it to half this value, the time constant reduces to half,
Okay.
and it'll be twice as fast.
Thank you. 500 ohm resistor and uncharged
1.5 microfarad capacitor are connected in series. What is the initial current? I guess and here's how you find the initial current. The initial current, well, it decays exponentially. The initial current is as if this wasn't present. Okay, anyway, here is the functional form of the current. It's V over R e to the power of minus t over tau, where tau is RC. Okay, and this is the initial current. At t equal to 0, this is 1. So the initial current is that. Okay. So in lab, we'll deal with a lot of milliamp currents. What is the time constant? So this is A. The time constant is RC. What does the time constant mean? What does it tell you?
Tells you how long it takes to charge the capacitor.
It tells you what is the time scale over which things change. The capacitor is charging, 65% of the capacitor is charging. Okay? So that's the time scale of the circuit.
Okay.
What is the time constant for us? About 25 years. For a human life, the time constant is about 20. That's a generational. Okay. What's the time constant for a butterfly? 10 days. Okay. So R is 500 ohms. Microfarads. Micro is 10 to the minus 6 farads. And again, in all these things, ohms times farad is what?
Second.
Seconds. Very good. See, this is a time constant. And okay. So this is 750.75 into 10 minus 3 seconds, 0.75 milliseconds. So things change in the circuit over a millisecond time. Okay. So if you wait 10 milliseconds, the capacitor is completely charged. Okay. What is the current after one time constant? So the current was V naught, V over R, e to the power of minus t over tau. And so they want you to find the current at tau. It's V over R, e to the power of minus tau over tau. So it's V over R, 1 over E. Okay. And I'll write down, let's figure out 1 over E. So this is what we mean. So you see it's dropped to 35% of the initial value. Okay. And the initial value we just found earlier was 12 milliamps. What is the voltage on the capacitor after one time constant? So the voltage on the capacitor is, what is this? A charging capacitor is charge is BC. So this is the charge on the capacitor as a function of time. That's the voltage of the battery, 1 minus e to the power of minus t over tau. And they want you to find out at one time constant so the voltage on the capacitor builds up to 63% the voltage of the battery, which is the voltage of the battery was 6.16 volts. Yep. This problem says using the exact exponential treatment, determine how much time is required to charge an initially uncharged 100 picofarad capacitor through a 75 mega ohm resistor to 90% of its final voltage. So here is the expression for the voltage. Voltage is the voltage of the battery, 1 times that. Okay. Okay, so for this guy, 100 picofarads, $75 mega ohms. So the time constant for our circuit is 7.5 into 10 minus 3. 7.5 milliseconds. All right. So the time constant is that, yeah, so if we measure the time in milliseconds, you can just put that number. Okay, so you want the voltage you want the voltage to build up to 90% its maximum value. And we're going to solve for t. So 0.9 equal to 1 minus e to the power of minus t over tau. E to the power of minus t over tau equal to 0.1 minus t over tau equal to log 0.1. T equal to minus tau log 0.1. Okay. And tau was 7.5 milliseconds. So after 17.3 milliseconds, the voltage on the capacitor will have built up to 90% its value.